What would you do if you discovered that something out there in the void of space just changed its course in a way that no one can explain? Stay until the end, because what you're about to hear could transform everything you thought you knew about the cosmos. This story begins in silence, in the infinite darkness that separates the stars, where an object has been traveling for billions of years. A traveler without a name, without a known origin, without an apparent destination, until now.
My friends, welcome once again to this corner where the universe tells us its secrets. I'm Felipe Suarez, and today I bring you a story that has me, I confess, with my soul hanging by a thread. Have you ever thrown a rock and expected it to change direction in the air just like that by its own will? Impossible, you'll say. Well, it turns out that something very similar just happened up there in deep space. Are you ready to discover it?
The object in question carries a technical name, a code that astronomers assign to it following international conventions. They call it 3I Atlas. The letter I, in this case, is not a whim. It's a designation that indicates something extraordinary, something that completely changes the nature of this visitor. It means interstellar. This comet, if we can call it that, was not born in our solar system. It did not form in the frozen regions beyond Neptune, where billions of fragments of ice and rock reside. It did not emerge from the Oort cloud, that invisible shell that surrounds our cosmic neighborhood. 3I Atlas comes from another place, from a corner of the galaxy that we will probably never know, from a star that perhaps no longer even exists. And yet, here it is, crossing our solar system like a luminous ghost, leaving behind a trail of mysteries that scientists are only beginning to decipher. The first observations detected it as a tiny point moving among the constellations, an almost imperceptible flash that only the most sensitive telescopes could capture. But as the weeks passed, as astronomers refined their calculations and pointed more instruments toward that fragment of light, a disturbing image began to emerge. This object was not behaving as it should. Its movements defied predictions. Its brightness fluctuated in unexpected ways. Its trajectory seemed to follow a pattern that no one could fully explain. In the heart of Mexico City, a telescope captured something that would make observatories around the world stop their usual routines. The images showed with extraordinary clarity the comet's tails, those ethereal structures of dust and gas that extend for millions of kilometers. But they also showed something else, something that shouldn't be there, an anomaly in the structure, a pattern too precise, too orderly to be the product of cosmic chance.
Do you know what troubles me most about all this, friends? It's not just that the comet does strange things, it's when it does them. Because it turns out that the most significant change in its trajectory occurred precisely when no one could see it, when it was hidden behind the sun, invisible to all the telescopes on Earth. Coincidence? Or is there something more that escapes us? I ask you, what do you think?
The trajectory of a comet is, in essence, a gravitational dance. The forces that govern its movement are known, predictable, mathematically precise. The sun exerts its constant pull, attracting the visitor toward its burning core. The planets, especially the giants like Jupiter and Saturn, add their own influences, small perturbations that can alter an object's course on timescales ranging from months to millennia. And then there is the comet's own activity, the sublimation of its ices when it approaches solar heat. Those jets of gas that act like small, unpredictable engines, pushing the nucleus in directions that depend on the geometry of the moment, on the chemical composition, on factors that sometimes we can't even measure directly. All these elements combine in a complex but fundamentally understandable dance. Astronomers have developed sophisticated models to predict the behavior of comets, equations that take into account every known force and calculate with precision where the object will be at any given moment. These models work. They have worked for decades. They have predicted the returns of periodic comets with astonishing accuracy. They have allowed space missions to intercept cometary nuclei millions of kilometers away. But with 3I Atlas, the models fail. Not dramatically, not with gigantic errors suggesting poorly made calculations, but in a subtle, persistent, unsettling way. Every time scientists update their predictions with new data, they find that the comet is not exactly where it should be. The discrepancy is small in absolute terms, barely perceptible in the vastness of space, but it is consistent. And the strangest thing is that this discrepancy seems to follow a pattern, as if something were guiding the comet toward a specific destination. That destination has a technical name. Astronomers call it Jupiter's Hill Radius. It is an invisible sphere that surrounds the giant planet, a gravitational boundary where Jupiter's influence begins to exceed that of the Sun. Imagine an immense bubble, more than 50 million kilometers in radius, floating in the void around the most massive planet in our system. Within that bubble, the rules change. Objects that cross that boundary enter Jupiter's domain, subject to its gravitational pull in ways that can dramatically alter their future trajectories. And 3I Atlas, according to the most recent calculations, is heading precisely toward the edge of that sphere. Not near it, not in its general vicinity, but exactly toward its boundary. The precision is the kind that makes mathematicians review their equations 3 times, looking for errors they don't find.
Friends, let me put this in perspective for you because numbers sometimes feel cold, abstract. Imagine throwing a dart from 100 meters away, blindfolded in the middle of a storm, and the dart, against all odds, hits right in the center of the target. That's what 3I Atlas just did. The odds? 1 in a billion, perhaps worse. Do you still think it's a coincidence?
The scientific community is divided, as usually happens when evidence defies expectations. There are those who insist that all the anomalies can be explained with known physics, that we simply need more refined models, better data, greater patience. These scientists point out, rightly so, that interstellar comets are fundamentally new objects to us. We have no prior experience with them, we don't know what to expect from their compositions, from their internal structures, from their histories of billions of years traveling through the galactic void. Perhaps, they argue, 3I Atlas is made of materials we have never studied, exotic ices formed under conditions of temperature and pressure radically different from those of our solar system, complex organic compounds that sublimate in ways our models don't contemplate, crystalline structures that react to solar heat in unexpected ways, releasing gases in patterns that seem orderly but are actually the product of internal geometries we cannot observe directly. It's a reasonable position, scientifically conservative, and probably correct in many respects. The history of astronomy is full of cases where apparently inexplicable phenomena eventually found perfectly satisfactory natural explanations. Pulsars, when they were first discovered, emitted signals so regular that some scientists joked about the possibility that they were alien beacons. They turned out to be rapidly rotating neutron stars, an extraordinary but completely understandable natural phenomenon. However, there is another faction in the scientific community, smaller but equally respectable, that argues that excessive caution can be as problematic as unbridled speculation. Professor Abraham Loeb of Harvard University is perhaps the most prominent voice of this group. He is not a marginal theorist or a sensationalist headline seeker. He is a scientist with impeccable credentials, hundreds of publications in specialized journals, almost a decade at the head of the astronomy department of one of the most prestigious institutions in the world. And Loeb has said something that makes many of his colleagues uncomfortable. He has suggested that the anomalies observed in objects like 3I Atlas and before it Oumuamua are so significant, so difficult to reconcile with known physics, that it would be scientifically irresponsible not to consider all possibilities, including those that make us feel uncomfortable.
Now, friends, before you think we've gone off into the clouds, let me clarify something. No one is saying that 3I Atlas is a spacecraft crewed by beings from another world. That would be jumping to conclusions without evidence. But the question Loeb raises is legitimate. How complete is our knowledge? Are we willing to keep an open mind? What do you think?
The images captured from the telescope in Mexico City add another layer to this mystery. They show with extraordinary clarity a characteristic that very few comets exhibit, an anti-tail. To understand why this is significant, we must first understand how normal cometary tails work. When a comet approaches the Sun, the heat causes the ices on its surface to begin sublimating, to pass directly from solid to gaseous state, without going through the liquid phase. These gases, along with dust particles trapped in the ice, are released into the surrounding space, forming a diffuse envelope around the nucleus called the coma. From that coma, two main forces act on the released material. The solar wind, that constant flow of charged particles emanating from the Sun, pushes the ionized gases in the direction opposite to our star, forming the ion tail, generally bluish and straight. Solar radiation pressure, meanwhile, pushes the heavier dust particles in a slightly different direction, creating the dust tail, typically white or yellowish and curved. Both tails, by definition, point in directions away from the Sun. It is a direct consequence of the physics involved, as predictable as the shadow cast by an illuminated object. But an anti-tail defies this apparent logic. It is a structure that seems to point toward the Sun, not away from it. In normal comets, anti-tails are rare but not unknown. They occur when particularly heavy dust particles remain suspended along the comet's orbit, and from certain viewing angles, these particles appear to form a tail extending in the opposite direction to the main tails. It's a perspective effect, a cosmic optical illusion, nothing more. But 3. I-Atlas's anti-tail doesn't behave like an optical illusion. It is too narrow, too defined, too stable. The images show an almost perfectly straight line extending from the comet's nucleus toward the Sun, as if someone had traced a laser beam across millions of kilometers of vacuum.
Have you ever seen something so orderly in nature, friends? The dust should disperse, it should form diffuse clouds, chaotic patterns. That's what physics predicts. But this anti-tail seems drawn with ruler and compass. What natural force can maintain such a structure? I confess that this part of the mystery is what keeps me awake at night.
Astronomers have proposed several theories to explain the anomalous anti-tail. One possibility is that the comet's composition is unusual, with ices that sublimate in ways we don't fully understand. Perhaps the crystalline structure of those ices produces perfectly directional gas jets, releasing material at very specific angles that create the illusion of order, where in reality there are complex natural processes that we simply haven't modeled correctly. Another theory involves magnetic fields. The comet, moving through the solar wind, could be generating or interacting with electromagnetic fields that affect dust distribution in ways our current models don't contemplate. Cometary dust particles often contain metallic components or minerals with magnetic properties, and under the right conditions, these particles could align along field lines, creating orderly structures that seem artificial, but are the product of known physics operating in regimes we haven't studied in detail. A third possibility, more speculative but not far-fetched, is that the internal structure of 3I Atlas's nucleus is radically different from that of comets in our solar system. If the object formed around a star very different from the Sun, under different conditions of temperature, pressure, and chemical composition, then its internal architecture could include channels, cavities, or deposits of material that produce highly focused gas emissions when heated. All of these are possible explanations. All deserve serious investigation, and scientists in observatories around the world are working day and night to test them. But here's the problem that keeps many of them awake. None of these explanations fits perfectly with all the observations. Every time a theory seems to solve one aspect of the mystery, a new piece of data appears that introduces a contradiction. It's like trying to assemble a puzzle where the pieces change shape every time you think you've found their place. Frustrating, yes, but also fascinating, because it suggests we are facing something genuinely new, something that will expand our knowledge once we manage to understand it.
Do you remember Oumuamua, friends? That was the first interstellar visitor we detected back in 2017. It also did strange things. It also defied our expectations. And it disappeared before we could study it thoroughly. Now we have 3i Atlas, and it's as if the universe is giving us a second chance. Will we take advantage of it? Or will we be left with more questions than answers again?
Oumuamua appeared without warning in October of 2017, detected by the Pan-STARRS telescope in Hawaii. Its name, in Hawaiian, means approximately messenger from afar arriving first, and it was an extraordinarily strange messenger. Its shape was unusual, elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a flat slab spinning through the void. It showed no visible tail, despite passing relatively close to the sun, which was strange for an object supposedly containing volatile ices. But the most disconcerting thing was its acceleration. As Oumuamua moved away from the sun, something was pushing it. Something that wasn't gravity. Something that couldn't be fully explained by the normal outgassing of a comet. The acceleration was small, but measurable, consistent, impossible to ignore. Astronomers proposed several natural explanations, none completely satisfactory, and before they could solve the mystery, the object faded into the darkness of interstellar space, too faint to be followed. And now, just a few years later, we have 3i Atlas. Another visitor from the galactic depths, another object that behaves in ways that defy our expectations. The similarities are unsettling. Both show anomalies in their trajectories. Both exhibit characteristics that don't fit neatly with our models of cometary behavior. Both seem to be following paths that take them close to Jupiter. That last coincidence is particularly interesting. Jupiter is the most massive planet in our solar system, a gas giant with enormous gravitational influence. Many objects, both local and visitors, interact with it in some way during their passage through our cosmic neighborhood. But the pattern that is emerging, 2 interstellar visitors, 2 trajectories that end up near the Hill radius of the giant planet, is the kind of coincidence that makes scientists stop and think.
Here I pose something that's been going around in my head, friends. What if Jupiter is serving as some kind of marker? What if there's a reason why these objects pass so close to the largest planet? I'm not suggesting cosmic conspiracies, of course, but the question is worth asking. What do you think? Is it pure coincidence, or is there something we're not seeing?
Human space missions have used Jupiter exactly that way for decades. It's called gravitational assist, and it's an elegant technique that allows space probes to gain speed or change direction using a planet's gravity as a boost. Voyager 1 and 2, launched in 1977, used Jupiter to accelerate their exit from the solar system. Without that gravitational push, they would never have reached the speeds necessary to escape the sun's influence. If an extraterrestrial civilization wanted to send probes across the galaxy, explore distant star systems, investigate unknown worlds, using giant planets to adjust trajectories would be a perfectly logical strategy. Efficient in terms of energy, predictable in terms of orbital mechanics, elegant in its simplicity. It's exactly what we would do if we had the technology to send objects to other stars. Now, before imagination runs wild, it's important to maintain perspective. There is no direct evidence that 3i Atlas is artificial. There are no radio signals emanating from it, no metallic structures visible in the images, nothing that screams spacecraft or alien probe. What we have are anomalies, behaviors that don't fit our models, patterns that seem too precise to be coincidental. That is not evidence of extraterrestrial intelligence. It is evidence that we don't fully understand what we're observing. And that distinction is crucial, because science doesn't advance by jumping to conclusions, however tempting they may be. It advances by accumulating data, testing hypotheses, discarding explanations that don't work, and refining those that do. The process is slow, sometimes frustrating, but it's the only method we have for getting closer to the truth.
I'll be honest with you, friends. Sometimes I wish I had immediate answers to know with certainty what 3i Atlas is and where it comes from. But science doesn't work that way, and perhaps that's the beautiful thing about all this. We are in the midst of the mystery, living the discovery process in real time. Doesn't it seem exciting to you to be witnesses to something like this? I think it does.
Observations continue day after day, night after night. Telescopes in Chile, in Hawaii, in the Canary Islands, in Mexico, all point toward that tiny point of light slowly crossing our sky. Each captured image adds information to the puzzle. Each brightness measurement, each spectroscopic analysis, each trajectory calculation, everything contributes to building a more complete understanding of what we're seeing. The telescope in Mexico City has proven to be particularly valuable in this effort. Its location, its technical capabilities, the dedication of the astronomers who operate it, everything combines to produce images of extraordinary quality. The photographs show fine details in the comet's tails, structures that other instruments can barely detect. They are precious data, pieces of the puzzle that could prove crucial when the time comes to assemble the complete picture. And there's something else the observations are revealing, something that adds another layer of complexity to the mystery. The distribution of dust around 3I Atlas doesn't follow expected patterns. In a normal comet, fine dust, being light, is quickly pushed away from the nucleus by solar radiation pressure. Coarse dust, being heavy, remains closer to the orbital trajectory, forming different structures. Over time, this separation becomes very evident, creating distinct tails with distinguishable characteristics. But in 3I Atlas, this separation isn't clear. There are regions where fine and coarse dust seem mixed, released at the same time from the same region of the nucleus, but then behaving in different ways that don't fit the models. It's a pattern astronomers haven't seen before, or at least not with such clarity.
Do you know what this reminds me of, friends? It reminds me of those cooking recipes we inherited from our grandmothers, where all the ingredients are listed but something never turns out the same. Here we have all the cosmic ingredients, all the known forces, and yet the result doesn't add up. Could it be that we're missing a secret ingredient, something the universe hasn't revealed to us yet?
One fascinating possibility is that 3I Atlas contains genuinely exotic materials, compounds that don't exist in our solar system or exist only in minimal quantities. If the object formed around a star, with chemistry different from the Sun's, in a region of the galaxy with different elemental abundances, then its composition could include ices and minerals we have never studied directly. Astronomers know, in theory, a variety of ices that could exist in interstellar space: nitrogen ice, carbon monoxide ice, methane ice, complex mixtures of these and other compounds. Each of these materials has different sublimation properties, different activation temperatures, unique gas release patterns. If 3I Atlas is made of an unusual mixture of these ices, that could explain why its behavior is so different from familiar comets. But there's a problem with this explanation. It doesn't explain the precision of the trajectory. It doesn't explain why the comet seems to be heading exactly toward Jupiter's Hill radius. Exotic ices can produce strange behaviors, yes, but they cannot produce millimetric course adjustments toward specific destinations. That would require something more, something current models don't contemplate. And here is where the mystery deepens, because when scientists look for natural explanations for that level of precision, they come up short. Celestial mechanics is deterministic, yes, but it's also chaotic on large scales. Small perturbations amplify over time, making it impossible to predict exactly where an object will be after millions of years of interstellar travel. And yet, 3I Atlas seems to have arrived at our solar system at exactly the right time, at exactly the right speed, to end up in exactly the right place.
I ask you a direct question, friends, because I want to know what you feel when you hear this. Have you ever experienced a coincidence so improbable that it made you stop and think? A moment where everything fit together perfectly, against all odds? That's what 3I Atlas represents to me. A cosmic coincidence that makes me wonder if they really are just coincidences.
The encounter with Jupiter is scheduled for March of 2026. There are still years to go, enough time to continue observing, to accumulate more data, to refine models and predictions. When that moment arrives, scientists expect the encounter to reveal crucial information about the object's nature. If 3I Atlas experiences significant changes in its activity as it approaches the giant planet, if it develops new tails, if it shows alterations in its brightness or in the structure of its anti-tail, all of that will provide clues about the mechanisms driving it. Jupiter's gravity will act as a natural laboratory, exposing the comet to forces different from those it has experienced during its journey through interstellar space. And if the object shows additional acceleration, similar to what Oumuamua exhibited, that would dramatically intensify the mystery. Because a non-gravitational acceleration near Jupiter would be extremely difficult to explain with normal outgassing. The distance to the Sun would be greater, temperatures lower, cometary activity should be less. Any additional push at that point would require a new explanation, something our current models don't contemplate. On the other hand, if the encounter is quiet, without special incidents, without additional anomalies, that would also be informative. It would suggest that the oddities observed so far are the product of proximity to the Sun, of specific conditions that won't repeat when the comet moves away toward the colder regions of the system. It wouldn't completely solve the mystery, but it would help narrow down possible explanations.
2026 seems far away, friends, but time flies. And when that moment arrives, we'll be here telling you what happens. It's an appointment I don't intend to miss, and I hope you don't either, because what 3I Atlas reveals to us could change our way of seeing the universe. Can you imagine being witnesses to something like that?
While we wait for that encounter, current observations continue to provide surprises. Astronomers have detected brightness variations in 3I Atlas that don't correlate with the expected rotation of the nucleus. Comets, like most celestial objects, rotate on their axes. As different regions of the surface become exposed to the Sun, outgassing activity changes, and this produces brightness fluctuations that follow predictable patterns based on the rotation period. But 3I Atlas doesn't show that pattern. Its brightness variations seem to occur almost randomly, intensifying and diminishing without obvious correlation to any measurable parameter. It's as if the comet had its own internal rhythm, a cadence that doesn't obey rotation or distance to the Sun, or any other factor scientists have been able to identify. One possibility is that the comet's nucleus has an extremely irregular shape, so irregular that small changes in its orientation produce dramatic changes in the amount of active surface exposed to solar heat. Imagine an object with protrusions and cavities, mountains of ice and valleys of rock, smooth surfaces alternating with porous regions. Such an object could show chaotic brightness behaviors even with perfectly regular rotation. Another possibility, more speculative, is that the comet's activity is controlled by internal processes we cannot observe directly. Perhaps there are reservoirs of volatile material buried beneath the surface, released sporadically when internal conditions reach certain thresholds. It would be like a geyser in Yellowstone, but on a cometary scale, unpredictable eruptions of gas and dust that alter brightness without following external patterns.
It's like trying to predict when a volcano will erupt, friends. We know it's going to happen, but we don't know exactly when or with what intensity. 3I Atlas keeps us in that constant uncertainty, revealing a little here, hiding a little there. Does that sound familiar? To me, it reminds me of those mysteries of life that we never quite fully solve.
The fine structures within the comet's tails are providing additional clues. High-resolution images show that the tails are not homogeneous, but contain streams and filaments, regions of higher and lower density that interweave in complex patterns. These structures suggest that the emission of material from the nucleus is not uniform, but comes from multiple active sources, each contributing its own flow of gas and dust to the surrounding environment. In a normal comet, these active sources correspond to regions of the surface where ice is directly exposed to solar heat. As the comet rotates, different sources become illuminated and activated, producing jets of material that create the structures observed in the tails. It's a well-studied process, documented in multiple comets over the years. But in 3I Atlas, the structures seem to change too quickly. New filaments appear and disappear on timescales that don't correspond to the nucleus's rotation. It's as if the active sources were turning on and off for reasons unrelated to direct solar illumination. This could indicate that the comet's surface is extremely heterogeneous, with regions of very different composition, alternating over short distances. Or it could indicate that there are internal processes, accumulated and released pressures, underground chemical reactions that control activity in ways we haven't contemplated before.
Do you know what image comes to my mind, friends? That of those dancing fountains they have in some parks, where the jets of water rise and fall to the rhythm of the music. 3I Atlas seems to be dancing to its own melody, one that we still can't hear. What do you think the universe is playing for this peculiar visitor?
As the weeks pass, more observatories join the tracking effort. The international astronomical community has recognized the importance of 3I Atlas, and resources are being mobilized to maximize the quantity and quality of collected data. There are proposals for observations with space telescopes, discussions about possible flyby missions, plans for coordinated analyses that integrate information from multiple sources. It's a truly global effort, transcending national borders and institutional rivalries. Scientists from dozens of countries, speaking different languages, working in different time zones, all united by shared curiosity, by the desire to understand this extraordinary visitor. There's something profoundly beautiful in that, something that says a lot about the best of our species. And at the center of it all is 3I Atlas, that fragment of matter that traveled for eons through the interstellar void, that passed near stars we'll never know, that crossed regions of the galaxy we can only imagine. Now it's here, in our cosmic neighborhood, offering us a unique window into worlds and processes that would otherwise remain inaccessible. Every observation, every measurement, every piece of data collected is a gift, an opportunity to learn something new, to expand our knowledge, to get a little closer to understanding the vast universe of which we are part.
And that, friends, is what moves me most about this story. It's not just the unsolved mysteries, nor the inexplicable anomalies. It's humanity coming together to observe, to ask, to seek answers together. Don't you think that says something beautiful about who we are? It fills me with hope.
There are questions that 3I Atlas will probably never answer. We won't know for certain what star it came from, nor how long it traveled before arriving here. We won't know what conditions prevailed in the disk of gas and dust where it formed, nor what catastrophic events launched it into interstellar space. Those are questions that will remain open, mysteries within the mystery, layers of uncertainty we may never penetrate. But there are other questions we can expect to answer. We can determine, with sufficiently precise observations, the chemical composition of the coma and tails. We can measure the rotation period of the nucleus, even if only approximately. We can track the evolution of activity as the comet approaches and moves away from the Sun. We can document the encounter with Jupiter and look for signs of changes induced by the giant planet's gravity. Each of these answers, however partial, will add to our knowledge, and accumulated knowledge over time will allow us to build a more complete picture not only of 3I Atlas, but of interstellar objects in general, of the processes that create them, of the trajectories they follow, of what they tell us about the galaxy we share. Because that's what interstellar visitors represent, ultimately. They are messengers from distant places, carriers of information about worlds we'll never see directly. Each one that passes through our solar system tells us a story, a narrative of formation and travel, of ice and rock, and the void between the stars.
I like to think of them that way, friends, as messengers, cosmic letters sent from remote corners of the galaxy, arriving at our celestial mailbox after journeys of billions of years. What are they telling us? We don't fully know yet, but the simple fact that they arrive, that we can see them and study them, seems to me an extraordinary gift. Do you feel the same?
The observation window won't last forever. Eventually, 3I Atlas will move too far away, its light will fade, and we'll be left with the data we've collected. There will be subsequent analyses, scientific publications, debates about interpretations, but direct observations will come to an end. The comet will continue its journey, moving away from our sun, entering once again the darkness of interstellar space, toward destinations only it knows. It's a bittersweet thought. We know this opportunity is finite, that every night of observation is precious, that we must make the most of the time we have. And that urgency, paradoxically, makes the experience more intense, more meaningful. We are living a unique moment in the history of astronomy, and we know it. Oumuamua passed too quickly. It was detected late, when it was already moving away, and it disappeared before we could study it adequately. With 3i Atlas, we have more time, more preparation, better instruments. We won't repeat the mistakes of the past. This time, we'll do things right. And when it's all over, when the comet is barely a memory and a set of archived data, we will have learned something. Perhaps not all the answers we were looking for, but something valuable, something that brings us closer to better understanding the cosmos of which we are part.
Do you know what I think, friends? That even if we don't solve all the mysteries, the attempt is worth it, because the search itself transforms us, makes us better observers, better thinkers, better human beings. 3i Atlas has already given us that, regardless of what we discover later. Don't you think that's already a lot?
The cosmos has a way of reminding us of our scale. We are small, ephemeral, inhabitants of a minor planet, orbiting a common star in the suburbs of an ordinary galaxy. But we are also extraordinary. We are the part of the universe that has learned to ask about itself, that builds telescopes and sends probes, that pursues understanding with tireless passion. 3i Atlas, that fragment of ice and rock that arrived from the galactic void, is giving us a gift. It is reminding us that there are more things in heaven and earth than are dreamt of in our philosophy. It is inviting us to look more deeply, to think more boldly, to imagine more freely. And perhaps that is enough. Perhaps we don't need to solve all the mysteries to benefit from them. Perhaps the simple act of wondering, of searching, of marveling is its own reward. 3i Atlas's journey will continue. It will pass close to Jupiter, continue moving away, eventually disappear into the depths of interstellar space. But the questions it has awakened will remain with us. And when the next interstellar visitor appears, because it will appear, we'll be better prepared to receive it. Until then, we'll keep observing. We'll keep asking. We'll keep marveling at the wonders the universe reveals to us. Because that's what we do. That's who we are.
And with that, my friends, I leave you for today. But before I go, I want to ask you something from the heart. If this story made you think, if it made you feel that spark of curiosity we all carry inside, subscribe to the channel. There are many more stories waiting to be told, many more cosmic mysteries to explore together. I would love for you to join me on that journey. And leave me a comment. Tell me, what part of this story reminded you of something from your own life? Have you had moments where the universe showed you something unexpected? Share your experiences, because we are all travelers in this immense cosmos. Until next time, friends, keep your gaze on the stars.